Hello.
So, hello, sir. Hello, everyone. Welcome to Advancing Northeast. This is Joshi Padge, your host for the day, and it is my privilege today to sit here and introduce you all with our distinguished guest, Mr. Sourabh Dube, Professor, Department of Physics, IISER Pune, a luminary in the field of experimental particle physics. So, I welcome you wholeheartedly. Yeah. Okay. Yeah. So thank you for making time, sir, and thank you for being here. And I'm quite enthralled right now. So I welcome everyone on this enthralling conversation, discussion that we are going to have, I'm pretty sure, on this captivating journey through the world of physics of science. So, sir, I'll hand it over to you.
Thank you. Thank you so much for having me on the show. I think this is a really important thing that you guys are doing. It's always nice to be for students and other people to be able to hear different opinions, before coming to a
Definitely,
decision or thinking about what they want to do. So I'm really happy
definitely,
to be
sir.
here.
Thank you, sir. And it's also great that because since our platform is targeted for the youths of Northeast, sir,
Mm.
so yes, so this is also like a bridge that we are trying to create between, all the national and international organizations in education, employment, anything, and our Northeastern students, so that we can also, grow in the globally and
Right.
internationally as well. Right, right.
Right.
So, yes, sir. So we'll just start with a little about you, just, your background, where did you study and everything. Please, sir.
Okay. So I'm basically from Pune. I grew up a little bit in the Middle East. My dad used to work as an engineer there. So about till fourth standard, I used to live in near Dubai in Sharjah. And then after that, most of my schooling has happened in Pune. I went to undergraduate college also in Pune at a place called Ferguson College. Uh, After that, I applied for a PhD in the United States. And then I moved for my PhD to Rutgers University, which is in New Jersey. After my PhD, then I went on to do a postdoctoral fellowship at the Lawrence Berkeley National Lab, which is in California. So it's the other end of the United States. And after about 11 years in the US, I moved back to India. I became a faculty member here at IISER Pune. And now it's been almost 10 years since I've been here, a little more than that, actually. So that's the journey in brief. I've been interested in physics for a long time. When I was younger, especially here in Pune, I don't know if you know, there is an institute called IUCA, which is the Inter-University Center for Astronomy and Astrophysics. So, aside from doing a lot of good science, they also do a lot of good outreach. So they encourage students to come for talks. They have telescope building workshops and so on. So, like all young students in Pune, I was very interested in astrophysics, but then when I started my PhD, I actually realized that I enjoyed experimental particle physics more. So then I,
Okay,
sort of went into experimental particle physics.
okay, great, great. So there has been a shift in your area of interest. But, sir, is
Right.
it somewhere also interconnected later also, experimental physics and astrophysics in any way?
It is connected in the sense that the base for all of this is a good foundation in physics. You learn all of the same things. A lot of the
Right.
things that we learned during a BSc and MSc is stuff that was discovered like 100 years ago. So, like or 300 years ago, like Newton and so on. So a lot of the foundation is the same. Uh, but still there are several differences that come in when you start to do research in this. So that's
Right.
also true.
Definitely. So the details and everything that absolutely differs. So, sir, this it has been a long span. You have a great area of expertise now and experience. So you studied abroad. So how did you get there, sir? What was the process and everything? If just a little information you can share. Yeah.
Correct. So one thing is true that certainly how we used to go about things from back then to now has changed. There is a lot more exposure. There are a lot more avenues to find out information. For example, the internet was only just starting out when I applied. Uh, and I did have a computer at home, but it was all this old dial-up thing. So it was not like you could, for example, YouTube wasn't invented yet. Uh,
Oh,
Today, I think if somebody is interested in pursuing higher education, whether it is in India or abroad, the first step is to do some homework yourself. Like, you should go to the websites of different institutes, try to see what they offer, try to look at the programs that they have. So programs means, is there a PhD program? What are the application requirements? Do they require two letters of recommendation? Do they require you to take any exams? For example, in the US, there is an exam that you take called the GRE, that's the Graduate Record Exam. In India, you would take the NET exam, for example, or JEST if you wanted to do a PhD in physics. So depending on where one wants to go, one should first do some homework and figure out what are the steps. After that, it is important to do all of this homework like at least a year beforehand, because some of these things take a considerable amount of time. Uh, then the other actually good thing that people should do is talk to seniors. So if you know somebody who's pursuing higher education, or you know somebody's friend who's doing this, it's always a good idea to reach out to them, talk to them what they did. This gives you a lot of information that then you can decide, how to put together what to do.
Right. Okay. So mental preparation and also, years of research is also very important, right, sir? Okay. Okay. So after that, sir, you also have a fair amount of experience in working, right? IISER happened later. So before that, what all were the areas?
Right. So when I started off, I went to do my PhD at this place called Rutgers University. The first couple of
Okay.
years, one has to do basic coursework. So these are all the foundational courses one takes, and then one does a qualifying exam, which is sort of tests all of your physics background and so on. Once you qualify that, then it is assumed that now you're ready to do research. So during my PhD, I worked on an experiment called the CDF experiment that was at a particle collider called Fermilab. So Fermilab is in a lab near Chicago. And at that time, that was the world's highest energy accelerator. So today, that is the Large Hadron Collider. But at that time, Fermilab housed the Tevatron. The Tevatron was the highest energy accelerator. So I did my PhD there. I lived out in Chicago for about 3 years. Uh, the work that I sort of do in particle physics, I mean, we should talk about it. But at that time, a lot of it is that you're learning how to do research. So, you have problem statements, you work with a lot of people, you're sort of learning the ropes of how to do. After the PhD, then when I moved to do my postdoc at Berkeley Lab, I switched experiments. So then I moved from the Tevatron to the Large Hadron Collider, and I joined the Atlas experiment. So this is another experiment that is at the LHC. And there I started to focus on searching for new particles, new hypothesized particles and interactions. So that has sort of been the core of my research goals, after my PhD to sort of pursue.
Okay. Okay. So, sir, is that facility, what you said, that lab and
The Fermi
everything,
Lab.
that is
Hmm.
exactly, sir. So that is not available in India. I'm just not aware. So, yeah.
Correct. So the way these large scale experiments work is that
Mhm.
typically one facility has the accelerator. Now, an accelerator is an expensive thing to build. So usually, multiple countries don't have this. So today we have the Large Hadron Collider, which is at CERN in Geneva. But before that, the highest energy collider was at Fermilab. And in fact, at the moment, there are a few other big lab facilities around the world. So, for example, there is the Bell experiment in Japan. There is Babar, which is at Stanford in California. There is at DESI in Hamburg in Germany. There is another collider there. So there are a few of these colliders around the world. And at these colliders, what you have is different experiments. So an experiment can be thought of like a company. So in that company, maybe like 100 or 150 institutes from around the world will contribute. So
Okay.
that means that right now, IISER Pune, for example, is a member of the CMS collaboration. So in India, there's about 13 to 15 places. So these are members of CMS. In the same way, when I was doing my PhD, my institute, Rutgers University, was a part of the CDF experiment. And so now all of these institutes come together to build the detector, and they all sort of collaborate on that experiment. So that's kind of the model. And
Okay, sir.
different collaborations will have different groups
Mhm.
of universities, and they're sort of in competition with each other.
Right, right, right. So very, very interesting that way, sir. So the learning is immense and opportunities are immense.
Right.
Right. Okay. Okay. Wonderful. Since, sir, I'm sorry because it's not a very area that I am very, expert on. So I have to look on the details and ask you again and again. But yeah, it's very
That's
interesting,
not a
obviously.
problem.
Yes, yes. So, sir, is there any particular incident or, any story that you might want to share that led you to, towards your interest in physics? Any story or anything that sparked this
To
interest?
my interest in physics. Okay, so I like to read a lot, and my favorite genre to read is science fiction. Now, within science fiction, there are lots of choices, right? You can have science fiction that is completely made up, like for example, like the Star Wars movies or Iron Man or whatever. But then there's also science fiction that is only a little fictional. Like it's based on at least some laws of science and physics that we know. Uh, so one such really good author that is my favorite author is called Isaac Asimov. So Isaac Asimov is the author of a series of books called the Foundation trilogy. Actually, Apple TV now has a TV show that's running on Foundation on that book series, and he's also the author of a series of books on robots. In fact, Isaac Asimov is the one who's invented the term robotics. So he invented that term, and he's written tons of short stories that describe how
Right,
robots
right,
are
sir.
and that
I
sort of
also
thing.
remember if he wrote something on psychology or so maybe or time. I do not properly remember.
So he's
Vaguely, yeah.
invented a word called psychohistory. So which isn't a real
Exactly.
field,
Yeah.
but he uses that in his books. And so because of that was my sort of introduction to science. And I would read all of these things in his books. Then I would try to find out from encyclopedia like what part is real, what part is not real. That was what sort of drew me towards physics in the beginning. I mean, I wanted to be on a rocket and off to space somewhere. So that was the initial motivation to sort of pursue physics.
Right, right. So the reason that I asked you this question is because, firsthand when we get into physics, or I was a science student, so I definitely I was not a very good, student, not a science material. So I could not comprehend physics and it just went above my head. But then obviously there are shows and books like Big Bang Theory and everything that I kind of enjoy, but then I do not know how to link. So yeah, it's also very interesting that way. So, sir, we'll change the trajectory again. I'd like to know in very layman language if you could explain that what is experimental, particle physics. If somebody, our audience watching us, enthusiast, who wants to specialize in this special area.
Good. So the simplest way to describe what experimental or let's start with what particle physics is. So in particle physics, our aim is to study what are the fundamental particles of our universe and what are the fundamental interactions. So fundamental means that you can't break it apart anymore. The simplest analogy that one can think of is think of the periodic table in chemistry. Right? We all know the periodic table. So we have, hydrogen, helium, then we have all of these rows and columns describing various properties. We say that everyday material is made of molecules and molecules are made of atoms. And so these atoms are of the periodic table. Now, suppose I decide to keep breaking things apart. So I can take an atom and an atom consists of a nucleus and electron. Nucleus is protons and neutrons. Protons consist of quarks. So the question is, how long can I keep breaking these pieces? Like, does it go
Okay.
down infinitely down, or at some point it says, no, 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 you can't break this apart anymore. If you can't break it apart, that thing is called fundamental. So an electron is a fundamental particle because you can't break it apart, but a proton is not fundamental. A proton is made up of quarks, but quarks are fundamental. So in particle physics, we try to answer the question, what are fundamental particles in our universe? Like what is everything around us made from? So that's question
Okay.
one. And question two is, once you know what these fundamental particles are, how do these fundamental particles talk to each other? So all of us know the electromagnetic force. So if I have a positive charge and a negative charge, they will attract, and two positive charges will repel. It turns out that this sort of positive negative interaction is the electromagnetic interaction. We are also aware of the gravitational interaction. So gravity is what keeps us stuck on Earth and keeps the Earth going around the sun and so on. But aside from these, there are other interactions that happen. There is the strong force, there is a weak nuclear force. So what are all of the fundamental interactions is also something that particle physics tries to study. So that means in particle physics, there are two questions. What are fundamental particles and what are the fundamental interactions? Which means how do the
Interactions.
fundamental
Right.
particles talk to each other?
Mhm.
In experimental particle physics, we try to answer these questions experimentally. So in a very crude or layman way, the easiest thing to think of is you try to keep breaking apart the particle till at some point you can't break it apart anymore.
So that is the
So that's the
fundamental one.
idea. And then
Okay.
of course,
Okay.
the allied thing is you have to also measure properties of these fundamental particles. Now, if I say
Mhm.
that electron is fundamental, somebody can ask me, okay, what is the mass of an electron? Or if I
Right.
say
Right.
that, top quark is a fundamental particle, somebody can say, what is the mass? How does the top quark behave? How does it decay? What is its spin? What is its charge? Etc. etc. So aside from discovering stuff, you also try to measure the properties of these fundamental particles.
Okay, okay. Quite fascinating, sir. So basically, everything we see around us, has a fundamental particle, right? So this study
Right.
it keeps on, yeah, immense possibilities and keeps on expanding and expanding, I guess. So, sir, are there any, major fundamental particles like major, or is it infinite that there are fundamental particles keeps going on?
No, so
Uh,
actually the list is quite limited. So there is
okay.
a small little diagram that you can draw. Uh,
Mhm.
there are 6 types of quarks, 6 types of leptons.
Okay.
Then there are 3 types of interactions, which result in 1, 2, 3, 4, 5 types of interacting particles. So the total list of completely distinct particles is 61. So that's it. There's only
All right.
61 distinct particles. But even
Mhm.
in those 61, there are things that you can sort of exploit. So I don't know if you've heard of antimatter. So like matter, there is something called antimatter. And so every matter particle has a antimatter partner. So by doing things like this, you can actually display all of that information in a very small sort of a piece. So the whole list is really not that large. It's fairly small list.
Okay, okay, okay.
Now that is very remarkable, right? Like the whole of our universe can be just made from this really,
Exactly.
really small list.
Yeah, we can
But
just
it's
sum it
not
up.
so surprising because if you look at chemistry and all of the things around us, we also see that the stuff around us is made from very, very simple things. Like if I take carbon, hydrogen, oxygen, nitrogen, I can make human beings. So, it's that simple. So it's the same sort of analogy that the fundamental list is small. From that, we can make a lot of crazy things.
Okay, sir. So we also have a fundamental particles that we cannot break any further. Further.
Yes.
Okay, okay. Just a not so serious question. So, sir, moving on. About your research area, if you could speak a little about
Okay.
your field or
So
your.
after I joined IISER Pune, we became a
Mhm,
member of the CMS experiment. So at the Large Hadron Collider, there are four
mhm.
different experiments. These experiments are independent. So in the sense that you can only be a member of one experiment at a time. Two of
Okay,
these experiments are multi-purpose experiments, Atlas and CMS, and two of them are sort of more targeted. One is called LHCb and one is called ALICE. In India, Indian institutes are members of two of these. Like some institutes are members of CMS and some institutes are members of ALICE. So here at IISER Pune, we have a CMS group. So there, what my research has focused on, so for the last 10 odd years, is to search for things beyond the standard model. Now, what that means is that the standard model is the name of the theory that today describes all of the fundamental particles and interactions. So standard model is just the name we give to that theory. It explains everything that we observe around us, and it does a really good job at this. It explains, so if you calculate using the standard model and then you go out and measure you doing an experiment, you see that the agreement between my prediction, that is theory, and experiment is right up to almost 10 decimal places. So the agreement is really, really good. But despite this, we know that the standard model is not complete. For example, some of the audience may have heard of things like dark matter. So there is no description of dark matter in the standard model. There is no description of gravity in the standard model. Then there are some other things like in the universe today, we observe that there is a lot more matter and there is no antimatter. The question becomes that why is that? Why isn't there a symmetry between matter and antimatter? Why do we see more of one and less of the other? So these are some open research questions that the standard model doesn't answer. To try to answer these questions, theorists will come up with new particles. So they will make a hypothesis that maybe particle of this type exists or a particle of that type exists. Somebody will hypothesize that maybe extra dimensions exist. So rather than the three-dimensional world that we live in, maybe there are more dimensions. As an experimentalist, what I try to do is I use the LHC collision data to try to answer some of these questions. Is there an evidence of this kind of a particle, or can I find some anomalous behavior in the data that can't be explained by the known theory? Those are the things that I sort of do in my research.
okay, okay. So you have students under you whom you guide, right?
Right.
So, whom you're looking
So
after. So,
right now in my group, I have about 4 PhD students. I have a
oh,
couple of master students and several undergrads.
Okay, okay, great, sir. So, your interest in this, did you specifically want to work in this field and that led you to IISER?
So interestingly, no. So when I wanted to start my PhD, I wanted to do
Mhm.
astrophysics. Uh, but there I had a very fun conversation with the person who became my PhD advisor later. So what he tried to do is, it's a famous story. I think it comes from a George Gamow book. But imagine that you become friends with an alien, and now you're texting with this alien, right? You're both sending each other SMSs, and you can't see each other, but you are texting with each other, and you became good friends. Now, at some point, the alien, writes to you and says, "Okay, can you describe yourself physically? How do you look?" So you say, "Okay, I have two hands and two legs. I have appendages, and I am sort of symmetric around a central axis." And the alien says, "Okay." The alien says, "Okay, what about internal organs?" You say, "Well, I have a heart that is in the left side of my body." The alien then asks you that what is left? What is the meaning of left? Left
Okay.
side.
Mhm.
So now your job is to describe to the alien what you mean by left. For
Right.
example, you could say that, okay, make two parts of your body and call one side
Mhm.
left and one side right.
Mhm.
But the alien may think of this side as left and this side as right, right? So how can you tell the alien in a completely unmistakable way how to define left? It turns out that this is a very deep problem in physics. It comes from whether all of physics is the same in our world and the mirror world. So, um, I don't know if you watch some sports. Suppose you watch a random football match. Okay, so you don't know any of the players in there. Suppose I showed you the football match regular, or suppose I mirrored the football match and showed you. Nowadays when people take photos with the selfie camera, usually it's mirrored. So, is there some way that you could tell whether it's a real picture or a mirrored picture?
Sure.
Now, the point is, if you know the person, of course you can tell
Mhm.
that it's a mirror image. But if you don't know the person, you will not be able to tell. That is because most of the laws of physics are symmetric under a mirror inversion. Like what happens like this can also happen in a mirror. In other words, if I'm playing cricket, there can be right-handed batsmen and there can be left-handed batsmen. There's no real difference between them, or tennis for that matter. So the idea is that, are there laws of physics that you can use to tell objectively the difference between what is left-handed and what is right-handed? And this was actually that conversation that this person had with me, my advisor, Sunil Somulwar. And he led me, to his office after a departmental tea party. And then he kept talking to me, he kept asking me these questions. And at the end of that conversation, I was so fascinated by, what the field was, that I told him that I would like to work in this area. And then he asked me that, do you know some programming? Do you know some quantum mechanics? I said, yes, I know both. And then he said, okay, let's start and, do some project. And so that's how I sort of got into particle physics.
Okay, okay. Wow. I am processing that information because that is also like how we confuse, that mirror objects, that left, right. So now that I think of it, right, we cannot objectively actually put into, articulate it. This is right, this is left. So it's very, very interesting, very fascinating,
It's very interesting. If you
mind-blowing.
see a cricket player that you've never seen before, and
Mhm.
somebody shows you a movie of it, then you can't tell whether that person is right-handed and they're showing the movie ulta, or the person is actually left-handed. And so
It's
this is a
also
very
kind of
interesting thing to
like
think about.
playing with your psychology as well. So quite interesting, sir. So that's how you got went your journey into IISER also. So if you could now brief us a little about IISER Pune, our
Right.
audience watching us who wants to do research further there. So it's for them also the process and everything. Yeah.
So, okay. Around 2006, 2007, where when the ICERs first sort of got started, at the moment, I'll have to count. There are, I think, seven or nine ICERs. The first ICERs that started were in IISER Kolkata and IISER Pune, and then very soon they were joined by other Mohali, Bhopal, Thiruvananthapuram, Tirupati, Bahrampur in Odisha. So now there are a few ICERs. The aim of the IISER concept is to have research being brought down to undergraduate students. So for a long time in our country, what happened was that research started being done in institutes where there were no BSc, MSc students, only PhDs. And where there were BSc, MSc students, there was only education. There is no research there. So to try to sort of bridge this gap is why the IISER started. Typically, the IISERs admit students for a 5-year BSc MSc program or a PhD program. So there are these two main things that happen. IISER Pune is situated in the heart of Pune. It's a small campus, 99 acres compared to the other IISERs. That's also because, we are in the city. You don't need to have like a school on campus. You don't need to have a hospital on campus, that sort of thing. The main program is a program called the BSMS program, which students can get into after 12th standard. So after 12th standard, they write an entrance exam. It is called the IISER Aptitude Test, IAT. You write this exam. It's a joint admission to any one of the 7 IISERs. So according to your rank list and your preferences, you are
Okay.
allotted an IISER. All IISERs focus on fundamental science. So the degree is a bachelor's in science degree, master's in science degree. Now these sciences can be depending on the IISER physics, chemistry, maths, biology, earth science, data science, economic science, and so on. There are no engineering degrees here. The aim is to cultivate pure science research amongst the undergraduate population. This is admission at the BSc MSc level. To get
Okay.
admission at the PhD level, there are several things. Typically, that depends on the department. So, for example, the physics department here at IISER Pune will take admissions through an interview. And to be eligible to give the interview, one has to have a reasonable rank in either the JEST exam or the GATE exam or in the CSIR NET exam. So these are some different entrance exams that students will give. If they have a high enough rank, they are invited for an interview. And post the interview, people get selected for the PhD program.
Okay. Okay. Great.
I can also say a
So,
little bit about the physics department here at
yes,
IISER
sir.
Pune.
Sure. Please. Yeah.
So the physics department here is pretty diverse. There's about 33 faculty members, and we study the very small things like particle physics to the very large, like cosmology or the universe. About half the department is experimental. So out of 33, 16 are experimentalists and 17 are theorists. There is a wide number of labs. So experimental research happens in things like molecular collisions, quantum qubits, measuring various properties of things, plasma physics, and so on. And in theory side also, we work across the board. There are problems in nonlinear dynamics, quantum information, cosmology, astrophysics, particle physics theory, gravitational physics, and so on. I think at the moment there are around 100 to 120 PhD students, like research scholars. And of course, there's a large number of BSc and MSc students. So that's sort
Okay.
of the
Okay.
summary of the physics department.
Physics department. Wonderful. So, sir, I hear that you are also associated with a lot of outreach, activities. You love doing outreach, and this is also basically outreach. So we got to know about the department and the institution. So, any outreach, projects, particular projects as such that you are associated with, if you can, give a little idea.
So in terms of large scale projects, I'm actually associated with 2 separate projects that are happening right now. And more than outreach, they are about pedagogy. So they are about improving the education system.
Study curriculum, teaching curriculum.
Correct.
Okay.
Teaching curriculum. It's about helping teachers teach better. So
Okay.
usually what happens is, teachers join a job and then they start teaching. And over the years, whatever they learn from practice. They learn by doing in the classroom. But sometimes it helps to have, whatever new inventions, new things that come up or different techniques in how to explain things to students. If we can take that methodology to the teachers, then the teacher's job is made easier. So they can start to teach better. So I'm part of 2 projects. One is only in Maharashtra and the second project called IRISE, that is a pan-India project. So at the
Okay.
moment
I
we are
rise.
working IRISE, IRISE.
Mhm,
So
mhm.
we are working in Maharashtra, Bihar, Uttarakhand, and we are going to try to sort of work in a couple of more states. So maybe Jharkhand, maybe Karnataka, something
Right,
like that.
right.
So our aim in this IRISE project is to work with school teachers, government school teachers, and try to give them modern tools and techniques that they can immediately start using in their classroom to improve, how science education is imparted to students. So, for example, things like how to teach critical thinking,
Hmm.
how to introduce hands-on activities in the classroom. Like all of us, right? Sometimes if you see some activity, you learn a lot better than just on a blackboard. So,
Right,
what
right.
sort of
Absolutely.
activities can be done that are based on the school curriculum? So, these are
Mhm.
some things that we want to do in the IRISE project.
Okay.
So these are two big outreach projects that I sort of am associated with. But in addition to this, I also like talking about particle physics. I mean, aside from this. So for that, I do various things. Either it could be talks that I give in schools and colleges. We've also, in this year, in 2024, we've started an Instagram page for my group. And so in this Instagram page, sometimes we'll post random pictures of, what the group is up to. Sometimes we post some educational content, like we've made a couple of videos for Women's Day in Science. Then we also did an activity for the National Science Day. So we try to do some of these things to sort of project the kind of research that we do to the outside world. I think it's extremely crucial for, uh, anybody to be able to understand what sort of research happens. Like the
Absolutely.
barriers to understanding should be really low. And
Hmm.
one of the important things is, the research that we do, it is funded by the government of India through taxpayer money. So every single person
Okay.
who pays tax actually
Ah,
deserves to know, what sort of research is happening in India. So I think
right.
it's really important that we communicate with them.
Absolutely, absolutely. So, reaching out to the masses, I mean, everybody ha actually has to know about, needs to know
Yep.
about science, I feel, should know at least the basic knowledge. Yeah, and you are doing a great thing there. So, you could also mention the username of the page so that audience, we can also follow
Yes.
it.
So the Insta handle is called Hepex Pune, HEPEXPUNE.
Capex Pune. Okay, we'll put it up in our comment section and
I'll
everybody
send
can.
you the I'll send you the
Yes,
URL.
sure. You can send me the link to the page. And also about the IDIS thing that you said. So it's not only for the research, research people. It's for government teachers, which is, I think, yeah, in
Correct. It's for
short,
government school teachers. That's the idea.
breaks the barrier. We also here have a program called Teachers as Career Mentors, our initiative,
Oh.
which, right, yes, we are where we train teachers to, become career mentors as well for their students. So I think
Oh,
that
I
is
would love to
also,
get that information from you. I mean, it would be really nice
right,
to
absolutely, sir. And if we could
get that.
also collaborate in any way possible, I think that would also be a wonderful idea. I mean, with the NEP in
Absolutely.
action, we can do all sorts of wonderful things with
Exactly.
education, right?
Exactly.
Right.
Yeah.
So yeah, that is a wonderful thing. So moving on, sir, back to, career prospects in physics, we would like to know that what all are the, major career areas, be it research or be it any other jobs and everything.
So the kind of careers that physics students can do sort of depend on whether one starts after an MSc or after a PhD. Usually a PhD is a nice time to think of, what sort of careers one would do, because a PhD will teach a student how to attack problems. The specifics of any job depend on what you learn in your PhD. So if I take the example of experimental particle physics, usually a PhD student will learn a little bit of statistics, little bit of machine learning. They will learn a little bit of electronics. They may learn a little bit of, programming, FPGAs and things like that. Now, depending on which of these skills they actually master, they can imagine looking for a job right after their PhD ends. So, for example,
Okay.
you can, if you know electronics really well, you can think of joining places like Motorola. I know a lot of people who've joined Motorola, but I also know people who've joined like, finance banks like Goldman Sachs, because they had some modeling experience and they could do some statistical calculations. So a lot of finding a career post your PhD depends on the experience that you gain during your PhD. This also means that once you say start a PhD, you're in the first or second year. If you want to do industry, it is up to the student to start to reach out and figure out what is going on. So one should have a LinkedIn page, start looking at the LinkedIn profile of different people, see what sort of background they had. Uh, Try to reach out to different people and ask them that, okay, what do you do in your work? What are your challenges? How do you go about doing this? And then try to acquire those skills during their PhD, and then that's what helps.
Okay.
It's usually
Okay.
not a good idea to just do your PhD. After it is over, then start to think, okay, what am I going to do with my life? The thought process has to start a bit earlier.
Bit earlier. Okay, so that kind of gives you the time. The PhD gives you the time and the expertise as well. Okay, I think that is a very crucial and important advice because the students who do their, graduate and postgraduate, they just consider that directly they'll jump ahead to find job or something without having an idea of the job market, right?
And a lot of students sometimes expect that there will be campus placements. See, the idea is fine of having a campus placement, but more than that, what a science career or what a PhD in any science will teach you is how do you attack a problem. So, for example, one of the things that any researcher normally does is that first they will do some homework, they will try to get some data, they will try to take this problem and break it down into smaller pieces and see, okay, has anybody attacked this, has anybody done this, has anybody done this. Then they will try to put it all together. They will talk to more people in figuring out what sort of previous literature there is in the field to do this. This approach towards problem solving is what somebody who has a PhD in science brings to the table. So any job that requires this is actually a really good thing. I know of several people, for example, who did a master's in physics and then have moved to do an MBA. So
Okay.
what sort of things that they bring to a project management thing is different than what an engineer will bring to that. So I think you can do whatever you want even after a science degree. It's not really limited to academics.
And nothing, is of no use. Everything you can just use it with
E-
mix it with your skills.
Exactly. That
Yes,
that's a
talking
really
of
crucial point.
right, right. So talking of skills, right now the main focus, the government is also quite, focusing on skills because of employment issues and everything, right? So what, according to you, are the main skills required in the field of physics? I would just generalize it. Yeah.
So, okay, so I kind of like this question that in terms of technical skills, I think everybody should know a little bit of programming, either Python or C++ or something. Everybody should understand how to visualize data. So, for
Mhm.
example, if somebody gives you, this is an expense report of the last 3 years, you should be able to turn that into the right kind of graphs, right kind of information that allows somebody else to visualize that information, whether it is expenditure, whether it is population growth, whether it is, uh, how the traffic flows in a city. All of this information, if you can visualize it, it helps you to understand it better. Typically, physics students should also have the skill, or they should develop the skill to do back of the envelope calculations. See, it is one thing to sort of study theory, but it is quite another to sit and calculate what things are. Simple questions like suppose I put up a cell phone tower in my city and I live say 2 kilometers away from it, and there's a dense concrete, buildings from here to there. What is the power that the antenna should have so that I get reasonable signal in my house? Now, nobody is saying that everybody should do an exact calculation, but certainly back of the envelope calculation, how much the antenna power drops off, how much if it goes to concrete, how much energy will you lose? These things, it's important for people to be able to do. Um, in terms of non-technical skills, I think it is really important for students to learn the ability to document the work that they do. See, a lot of students do a lot of good work, but they forget to write down things. So then at the end of the project, now they are trying to scramble to write down some 10 pages. What happens then is that you miss a lot of the good stuff that you thought of during the whole process. So you have to learn to write something every day. Similar to that is also the ability to make short and long presentations. So it's very
Okay.
important for students to learn how to be able to put together all of your ideas in a coherent story way. So if I work on some project, typically it's not that I will directly find the answer. First, I'll try one thing, maybe it doesn't work. Then I try something else, and I try something else, and I come to the end. Now, when you're delivering a presentation on this, you don't have to go chronologically. You don't have to say that in the first week I tried this, then in the next week I tried this, and so on. Instead, it's important to build a nice story that this is what the motivation was, this is what some people have done before. I tried three things, but this is the thing that worked. Making that good story is a really important skill. A couple of other skills that I sometimes think that science students have less of is that people should be willing to put themselves out there and have conversations, in the sense that suppose you go to a conference and if you talk to only one person there, that's not helpful. You have to be able to go up to a stranger, introduce yourself and have a small conversation, or you have to be able to take part in a discussion some other people are having and just try to learn something from there. This skill is really really crucial because in the real world almost nobody has the time to sit you down, give you a textbook or explain something on the board. You have to learn on the job. You have to, anybody who works, like you work right now at this company. So you must also know this, that all of the learning happens when you're given a task. Somebody tells you,
Absolutely.
go do this, and now you have to learn. So this is a skill that is important for science students to sort of develop, the ability to talk to people, to learn while doing, rather than sitting and learning beforehand.
Okay, okay. So not only pen and paper, you just have to go there. Also, this is just, I think it's a little stereotype also that the science people, they do not really like interacting. They're just busy with their books and theories and stuff. So I really
It's
think
a
that
bit of a
talking to,
stereotype. I mean, yeah, some
yeah,
people do like, but
yeah,
it would be nice if more people are able to talk.
able to, yes, sir. Like you are doing, and you are, it's so cool talking to you. It's so nice that, that stereotype is completely best here. So yeah, this skills I think are very important for any say. So, sir, when this transition period from academics, like you said, from PhD, they can further look into the job market. So, what do you think that how this transition period also, like from academics to the job market, when they shift, any points that you have to you want to throw in there that
Hmm.
because
So
that is
actually,
also
this
quite
is,
different from academics to the
yeah,
job market, right?
it is actually quite, it's quite interesting. I mean, students
Mm-hmm.
need to do a few things. Like one thing is, they should build good web pages for themselves. They should put things on
Yes.
GitHub or something. It's,
Okay.
it's important to do good work, but it's
Mm-hmm.
also important for you to be able to showcase your work to other people. So, suppose you write to
Mm-hmm.
somebody on LinkedIn that I'm looking for a position, and by
Mm-hmm.
chance that person replies and they say, okay, can
Mm-hmm.
you show me a sample of your work? You should very quickly be able to point them to like a Git page or a web page or send them some report or something. So this has to be ready in hand. So that is one thing. Uh, the other thing about sort of joining industry is that there are actually large parts of certain domains that are under sort of utilized by scientists. So for example, actual research in education. So I don't mean just how to, I mean how to teach. What are better methodologies to teach and so on. So doing active research in education is something that, scientists, aside from their core research, this is something they can do. There is certainly the idea of media, right? Whether you are putting out the written word, whether you're making videos. There are a couple of these really good channels. For example, Veritasium is a very nice channel on YouTube that makes scientific content. There is no reason why
Yeah.
more people can't put out more of this content. You make a few animations, you take a simple concept, try to explain it. This is actually a really interesting field that people should try to get in. Um, Broadly, in India, the challenge is that science students have to still convince industries why they're useful. In a lot of developed
Okay.
countries, industries already know this. So a lot of companies in the US, for example, will hire MS and PhD people. In India, that trend is a little low right now, and we have to actively work on making sure companies see the value of bringing on these critical thinking, problem-solving people, and how it will benefit both the scientists, of course, and also the industry itself.
Okay, okay. Wonderful points you have highlighted there. I think very, very critical and important areas, and it will be very beneficial for our audience watching. So, sir, moving on, in this particular field, any major, scholarship, fellowship opportunities, particular names if you can point out, yeah.
So yeah, I'm not the best person to answer this, but certainly within India there are things like the CSIR net exam. So if you get a good enough rank, then either CSIR or UGC they will fund you to do a PhD for 5 years. So for sure those are exams students should write. If we talk about abroad, so in India there's also the Inspire Fellowship, which you can actually get after 12th standard if you're doing science. So that's a fellowship that you can get while you're doing a BSc, while you're doing MSc, and while you're doing a PhD. So certainly looking into the Inspire Fellowship is important. Um, in Europe, for example, there are a couple of ones. There is one called Erasmus Mundus, which supports, I think, PhD as well as master's education. In UK, there is the Newton Baba Fellowship. Uh, there are a bunch of these fellowships that different countries have. Of course, it's important that a lot of these are very competitive. So sometimes one has to plan it from much beforehand, investigate, and have like a couple of attempts before one manages to secure it.
Right. Okay. So because the information, is scattered everywhere, so the students also find it quite hard, to
Yeah.
where to find the right information in the pointers. So yeah. Also, sir, another area that AI is something that is coming up, in a huge way. So regarding that, any, how do physicists, if they want to do research, connect physics with AI. What do you think? Any say on it, sir?
So, see, the standard stuff is always there, that they need to be well versed in programming and current modern
Yeah.
libraries and that. But
Mhm.
one thing to realize is that the field of AI research is a very rapidly evolving one. So
Right.
that means for students, reading a lot of papers is very, very important. So
Okay.
they have to try to keep abreast of what is happening right now. Now, it is not that when one reads a paper, one has to understand it completely, right? That would be very difficult. But you need to be able to read papers and quickly classify them into, okay, this paper talks about a new technique or a new idea or a new approach or something. So that later on, when you need, you have this ready-made sort of bibliography of handy papers. It's also important to understand that because this field is very popular right now, many of the papers are not that impactful, right? Because things are very
Yeah.
rapidly evolving. People will do a quick study and then try to publish it. This is okay. This is how any field evolves. But this also means that students have to read a lot more. They need to quickly read things and decide, look, this is something really new and original. I need to spend time on this versus thinking, okay, this was something that I already read, like, in the paper 2 weeks ago. I don't have to
Right.
read this very carefully. This is kind of very important. One last thing about, which is applicable to AI research, but it's also applicable to a lot of other things, is that at least half of the time students every day should spend doing something, not reading, but doing. See, what happens is you attend a workshop, you attend a talk, you read a paper, and you spend like 5, 6 hours of your day doing this. And at the end of the day, you think that, okay, today was a very productive day. I did so many things. But actually, that's not true. This is all in support of you actually doing something. The example that I would give is, suppose you wanted to become a good carpenter. The only way to become a good carpenter is if you start, hammering things and cutting wood and so on. You can read a lot about what are the different kinds of woods like cherry trees and oak tree and maple tree. You can read up about, which hammers are great and whatnot. But nothing actually replaces the act of cutting wood and nailing. It's the same in any field. Half of your time has to be spent doing something, not just absorbing knowledge that other people have produced. That's good. But you also have to learn to start to produce knowledge yourself. That's very crucial.
Wow. Yes, sir. That hit quite hard. That was the limelight of the show for me. I'll give the act that we want to do. So absolutely. Thank you. Thank you for your wise words. And I think we have almost, covered everything that we wanted to know, I think. And I also have a good idea now that, I am aware now. So I think this way awareness should, go across people who are not from the field of science, but then you get to learn so much, and then you can word of mouth marketing is also one thing, and then others will also know, and then you can maybe have more people in science, right? So, sir, lastly, just about the job marketing, like because you studied abroad, so you have seen the job market there also. So, what do you think? Like you said that the science people, find it hard to explain that how do they, make use of themselves. So how do you see the difference here and there? What do you suggest, like students opting for working in
So,
abroad? Yeah.
honestly, okay, so there are two things. One is whether one
Mm-hmm.
chooses to work abroad or work in India.
Mm-hmm.
Um, that is a very personal choice in the sense that depending on, see, for some people, it is important that they give back to the place where they came from. For some people, it is very important that they, for example, live in a place that has a good climate. For some people, it will be good schools, so where one chooses to live is a very personal decision. But in terms of whether opportunities exist or not, I think even in India, we are improving quite rapidly because now we have an economy that is growing pretty well. We have a lot of industries that are competing with each other. The nice thing about this is this means that if you can do something for a company that puts it at a slight advantage, then they're very happy to take you on. The question becomes that how do you get your foot in the door? Like, the first step is the hardest step where you have to reach out, have to try to convince them to give you a chance. This problem is a little bit difficult. I mean, so one has to write to more people, one has to network.
Network a
So, for
lot. Yeah.
example, find alumni, through them, try to investigate what it is and see that you at least get an interview where you can then demonstrate why you fit right for the task. But it is changing for sure. There are a lot of places in India that are now actually hiring. So, for example, um, One of my ex-students, he did a PhD in particle physics, did also a postdoc in physics, but now he is working in a company to try to catch bank fraud, for
Oh,
example. So he's writing
okay.
machine learning algorithms to try to do bank fraud. I have another student who, not in India, but he's living in the UK. He's joined a company that does radio frequency instrumentation for talking with satellites. So the fields are very diverse, and a lot of it depends on what skills you learned. The thing is that it's important for students not to feel that, I finished my education, now I look to a job to settle in. So that is very tricky. Most of the time, something that the engineering students, for example, understand very well is that you have to hop a few jobs before you find the job that you like. So it's not like, you finish your PhD, now you decide, okay, my career is now going to be this. It's not that. You take one job, you learn some things there, then you try another. And it may be 2 or 3 jobs before you find something that you really like. And that's okay. That's part of the process. Rather than assume that you immediately get something that pays you a lot and you really like the work. That's very rare. You have to
Yeah.
sometimes look around a little bit, try out a few different things before you find the niche that works for you.
Yeah. I think that is also one reason, sir, that the youths are so disappointed today, mostly because they just want to run and rush and settle in. So yeah, to remember that is very important. So lastly, sir, any advice that you or message that you want to share for everybody watching us, also especially for the youths of Northeast. So have you been to Northeast, Assam?
So I've
Uh,
been to IIT Guwahati, of course. I spent
yeah.
some time there, and I actually have a couple of students I worked with have been from Assam. So one of them is from Shivsagar. Uh,
Okay. Yeah.
but I
Then I
would
know.
really like to visit for longer amounts of time.
Yes, sir,
You
you should surely
even
come,
aside from
and
Assam,
yeah,
even the other states, for sure.
yeah, you
I
should
mean,
also visit Netti someday. We'd love to host you.
oh,
It's
absolutely.
wonderful.
I'd be very happy. So,
Yes, sir.
okay, advice. I thought
Yeah.
about this. I think if I have to leave with one piece of advice for especially young students, it's that uh, one should have fun. What I mean is that, sometimes one gets too focused on the career side. You ask questions like, is this going to be helpful for my career? Will this look good on my CV? Is this a good opportunity? Is there scope in this field? Look, these are important questions to ask, but much more important is you should also start to ask that, will I enjoy doing this work? Do I care about this work? See, a career is a very fickle thing. It's very difficult to plan out things 5 years, 10 years in the future. That, I'm going to do this, then I'll do this, then I'll buy a house, then I'll buy a car, then I'll get married, and so on. It's difficult to plan things. We should worry about it a little bit, but we should also accept that a career is not in our control. What is in our control is, am I getting to work on things that are satisfying me today? If you get up in the morning, do I feel happy to go into work? Do I feel like, oh, today I'm going to get to do this and that's so nice? If you do that, if you enjoy the kind of work that you do, then you naturally do better at it. And if you do better at it, naturally that means, you sort of progress faster, you do better things. But it does start a little bit from you wanting to enjoy the kind of things that you're doing. I think that's important. I'm not saying don't worry about career. You should worry about career, but also start to worry about, whether you're having fun while you're doing it or not.
So worry and fun goes hand in hand. Yeah. Thank you, thank you. This verse I'll also take home, and I'm sure everybody watching us loved this session. It was so insightful, so you
Thank you.
know, for me it was I learned a lot. So thank you so much, sir. It was wonderful, and we'd like to have more such, more interactions, more collaborations in the near future. And yeah,
Absolutely.
we'll for everybody watching us, if you have any, if you want to know anything more, if you want to connect with Sir personally, I think we can also do that. He
Yes.
could be a virtual mentor for you.
Absolutely.
Yes. So yeah, we can do that. Thank you, sir, again for your time, and just end the session now.
So one thing.